my name is Alex, I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. A heads up right at the beginning, the contents of this video apply to spark ignition engines only, they don't apply to diesel engines. Also, the contents are more design or configuration related and may not be the typical maintenance problem. Anyway, in this video I'd like to share with you some findings that I could come up with during a long and exhaustive troubleshooting that kept me busy for some weeks. The problem dealt with sporadic pre-ignition in this new and custom V8 engine here that has a very high compression ratio of over 10:1 and uses air-fuel ratio control along with catalytic converters. Sorry guys, I have no video material of the actual pre-ignition events to show you here. That's because the problem was of a sporadic nature and hard to catch, on video as well as with test gear. Furthermore, this particular ignition system is now reconfigured and rid of its faults, so I cannot rebuild the faulty configuration anymore without major effort. But I'll show you some test gear graphs later in the video. There are some informations around about pre-ignition in combustion engines. However, if you look up the causes for pre-ignition, you'll probably find the classic explanations a bit hazy. Surely they may apply to certain cases, but in my opinion, they have a somewhat mythical aftertaste. But please judge for yourself after you watch this video. The most commonly given explanations for the cause of pre-ignition are a glowing spark plug electrode, or generally too hot a spark plug. Loose carbon deposits in the combustion chamber striking sparks. Hot protrusions in the combustion chamber, or generally too hot of a cylinder head. Sometimes a lean mixture is mentioned too, mostly however without explanation why it accompanies pre-ignition. Now, be that as it may, and let's put those classic explanations aside. In contrast, here I want to prove to you pre-ignition by parasitic sparks. This is what I found to be the cause for this engine's former pre-ignition problem. Strangely, I didn't read or hear about this process yet, even though it is pretty obvious once you've seen it. But now, let's take a look. Let me show you in general what pre-ignition typically behaves like with this graph here. We are dealing with a running multi-cylinder engine. If pre-ignition takes place, what's usually observed is a more or less sporadic flame in the intake port. Nothing in the intake port can possibly ignite the flame, so consequently we are dealing with a situation with a more or less open intake valve when some kind of problem in the cylinder pre-ignites the fresh charge. The flame burns from the combustion chamber up as far as it can get. Hopefully not an engine fire results and the flame extinguishes from lack of fuel up here. Still, what follows is that during this cycle in this cylinder, there is only burnt charge that doesn't ignite anymore at the power stroke and so doesn't provide network to the crankshaft. As a consequence, the engine runs notably rough, vibrates and coughs through the intake port. But pre-ignition is not limited to happen during the intake stroke. In severe cases, it may even take place during the early phase of the compression stroke, when the intake valve is closed. This can be catastrophic, since a violent counter-torque at the crankshaft will result. Now, pre-ignition may take place regardless if the engine is equipped with carburetors, mechanical or electronic fuel injection, or even direct injection. It also doesn't matter much if the engine is naturally aspirated, turbo or supercharged. However, parasitic spark pre-ignition can only take place if the engine has more than 2 cylinders. The sporadic nature of parasitic spark pre-ignition makes it practically unidentifiable with dedicated test gear such as this fine 1985 Bosch ignition tester here. But even if you use modern test clips and the lab scope to store the signals, parasitic spark pre-ignition can hardly be identified because its magnitude is similar to the noise that we pick up with the test gear. Furthermore, our testing result in this regard is strongly dependent upon the clip's location on the ignition wires. I assume these are the reasons why parasitic spark pre-ignition is not a commonly known process, even though it can be provoked in most engines. In the engine of the video's intro, I could find parasitic spark pre-ignition only via indirect testing. Now, how does parasitic spark pre-ignition happen? The potential for it is very much increased with bundled high voltage wiring. Now, you'll probably say, what's the fool talking about? I've seen bundled high voltage wiring on perfectly fine engines. That's right. You can find bundled high voltage wiring on car, racing and even aircraft engines. Even the iconic Porsche 917 and Cosworth DFV engines had bundled ignition wiring. But keep in mind the word potential. Bundled high voltage wiring provides a strong potential for parasitic spark pre-ignition. This, along with two other conditions, decides if parasitic spark pre-ignition will actually happen. Now, let's take a look at the parasitic sparking rig. It's not a beauty because it was manufactured from an old closet door. But luckily that doesn't matter so much. Let's start here with the ignition coil. It is driven with a primitive circuit which continually actuates this ignition transistor here, similarly as in a running engine. The ignition transistor repetitively connects and disconnects the ignition coil's primary winding to ground. The primary winding's other terminal is connected to 12 volts here. Very basic and very typical. The coil's high voltage terminal is connected here to some standard spiral core wire of typical length. This wire ends here abruptly. Next, we have an adjustable gap. The electrode is connected back here to ground to close the circuit. Now this here is the interesting part. We have a loose end of standard spiral core high voltage wire, which also ends here abruptly at an adjustable gap. The electrode is also connected back to ground. Now let this here represent a cylinder of our engine at the beginning of the power stroke, firing its spark plug. And let this here represent another cylinder of the same engine, which at the same instant works the intake or compression stroke. At the beginning of the power stroke here, the spark plug electrode should be surrounded with high pressure air-fuel mixture. Now, we don't have that here for simplicity of the rig, but we may qualitatively simulate this with a long gap. The air-fuel mixture under high pressure acts as an electrical insulator. The higher the pressure in the combustion chamber, the better the insulation between the electrodes. A long gap here causes high resistance, which electrically gives the same result. During the intake or compression stroke here, the spark plug electrodes are surrounded with part vacuum or low pressure air-fuel mixture. We may qualitatively simulate this with a short gap. Keep an eye on this spark plug gap here, which I pre-adjusted to roughly 1 mm as on typical spark plugs. Now, let's see what happens. Now what we saw here were parasitic sparks. Those sparks can be able to pre-ignite the fresh charge in this here cylinder. You probably noted that the closer the two wires are to each other, the stronger the parasitic sparks. So it seems that the parasitic spark energy is transmitted from this wire and received at this one here. but rather I prefer a different explanation, namely that the two wires form a capacitor. We know that capacitors block direct current, but they more or less pass alternating current. The quicker the alternating current and the higher the capacity, the easier the passing. Let's call it capacitive leakage. Now, if this is our capacitor, capacity equals two constants multiplied by plate area A and divided by distance D. Now consider A as the projected surfaces of the wire's conductors and D as the distance between the conductors. What we learn from this is that it doesn't matter if the two wires are just close at one point. Rather, it matters if a large projected area, that is length multiplied by conductor diameter, is close. Let's check this. So the experiment fits our capacitive leakage theory nicely. And on the side, we may conclude that for a given wiring pattern, the larger the effective conductor diameter, the stronger the potential for parasitic sparks. This is an interesting point here, because the effective conductor diameter of modern spiral core wires can be quite high. If you already heard stories about cross-arcing between ignition wires, here's the opportunity to check on this. Let me place the wires very close to each other, but still with a visible gap, while making sure we fire a parasitic spark. Then check if you can see a cross-arc somewhere here. Well, I didn't see any cross-arcing even with the favorable conditions here. Cross-arcing may be possible, but it seems in case of pre-ignition that the capacitive leakage theory is more realistic. Now let's see what happens if we increase our engine's compression ratio. In this case, the isolation at this spark plug gap here increases because of combustion chamber pressure. We simulate this with an even longer gap. At the same time, the insulation at this gap here remains pretty much the same, because at the intake stroke we typically have part vacuum here, even in high compression engines. So now it is even easier to generate parasitic sparks. The whole setup became notably more susceptible. Why is that? What results from better insulation at this spark plug gap here is higher peak voltage in this wire. As a consequence, for a given capacity between the wires, we leak more electrical energy, resulting in higher potential for parasitic sparks here. In other words, the higher our engine's compression ratio, the more potential we have for parasitic spark pre-ignition. A similar effect can be observed as air-fuel mixture is changed. The air-fuel mixture influences the electrical insulation at both spark plug gaps. What we can observe on real engines is that the less rich the air-fuel mixture, the more susceptible our engines become to parasitic spark pre-ignition. Due to mixture, this may be because of less insulation here, or because spark quenching is less effective, or because minimum ignition energy becomes less, who knows? It is hugely complicated to dig up this root even further. But for simplicity, let's keep in mind that the less rich our air-fuel ratio, the more potential we have for parasitic spark pre-ignition, just like before with increasing compression. At this point you may think, then why not shield the high voltage wires to inhibit capacitive leakage between them? Well, if we shield the wires, we still have capacitive leakage, but in this case to the shielding. Let me demonstrate this with this improvised half shield here, which is connected to ground. Obviously we may lose quite some ignition energy, as we see even with this half shield here. So shielding is probably not an elegant solution to our problem at hand. It seems much more elegant to separate and/or shorten the high voltage wiring as much as possible. The most modern coil-on-plug ignition systems with one coil on each spark plug seem to solve the problem permanently. But even these systems have weak points which may enable parasitic sparks. If you still doubt parasitic spark pre-ignition, let me show you even more evidence for it. This here is a test gear graph from the Intro's custom V8 engine. As we know from before, this engine is highly susceptible for pre-ignition because it has a compression ratio of over 10:1 and it uses catalytic converters, which means it is not operated with rich air-fuel ratio. Now, the blue trace shows the intake port pressure of one particular cylinder over time. Don't confuse this with combustion chamber pressure, it is intake port pressure. The red trace is from an inductive sync clip. It spikes with every ignition event in the engine, not just with ignition in our particular cylinder. When the intake port pressure falls, our cylinder works the intake stroke, sucking air from the intake port. This little pressure spike up here, by the way, is because of exhaust gas pressure. After intake follow compression, power and exhaust stroke until all happens again. This particular spike here, for example, indicates the ignition event in our cylinder. Everything with this graph looks fine and regular, doesn't it? Except of this here. This is one of the former sporadic and hard to catch pre-ignition events. It happened when the cylinder experienced part vacuum, which, as we know from before, is a favorable condition for parasitic sparks. At this instant, when the trace deviates, a parasitic spark ignited the fresh charge in the cylinder. This we see as a rise in pressure due to the expanding gases which escape through the intake port. But take a close look at the timing. If you compare it with our sync trace, you see that it coincides with an ignition event. And with our engine's firing order, we can identify from which other ignition wire the energy for the parasitic spark leaked. Now if you say, oh, the match timing here is just coincidence. I have more than just one graph proving this. And if you still say that's just coincidence, our intro's custom V8 engine had an initial ignition system configuration which led to a pre-ignition nightmare. On cold winter days, occasionally it even suffered from pre-ignition at a compression stroke during startup. This was very violent since it caused combustion when the intake valve was already closed and the piston was moving upward, still far away from top dead center. A violent counter torque at the crankshaft resulted, which during startup acted against the starter. Exhaustedly, I lost a few flywheel teeth during troubleshooting this problem. Here, after weld repair and before remachining. But the point here is that the broken teeth were spaced exactly 90 degrees apart on the flywheel. If you ask for my opinion, no classical pre-ignition explanation fits this, particularly with a cold and new engine. Here, I think only parasitic spark pre-ignition theory makes sense. It's hard for me to believe that I'm the first to identify parasitic spark pre-ignition. But then again, I don't understand why I couldn't find anything about this process in textbooks yet. Anyway, just a note at the end. Capacitive leakage between high voltage wires is not the only process that can cause parasitic sparks. During my troubleshooting, I was able to find 3 more processes aside from capacitive leakage. The latter, however, seems to be the most dominant one. If you're interested, let me know and I'll think about making a video about the 3 other processes. Well, I hope this video will be helpful to the one or the other among you having pre-ignition trouble. As always, thank you for not being bored to death. I appreciate your time. All the best for your engine projects and thank you.